In the last section, we studied the preparation of alcohols. Alcohols can be prepared from alkyl halide by a substitution reaction, from double bond by hydration reaction, from carbonyl compounds by reduction reaction. In this section, we're going to study the reactions of alcohols. The reactions of alcohols are the opposite of the preparation. So alcohols undergo elimination reaction to double bond, undergo substitution reaction to alkyl halide and ethers, oxidation reactions to carbonyl compounds. First, we go over the substitution reaction to alkyl halides. I hope you still remember the preparation of alkyl halides from alcohols. A tertiary alcohol reacts with hydrogen chloride, hydrogen bromide, give you the product. The reaction is SN1 mechanism. First, the poor leaving group hydroxide is converted to a better leaving group water. Leaving group leave give you the carbon cation, followed by nucleophilic addition give you the substitution product. Can you draw the detailed mechanism? Let's draw the mechanism. First, the alcohol molecule, hydrogen chloride, draw arrow, show lone pair electron of oxygen attack the hydrogen. Another arrow show the bond between hydrogen chloride break, electron go to the chlorine. Now hydroxide becomes a better leaving group OH2. Oxygen has a positive charge. Okay. Arrow show the bond break, leaving group leave, forms carbocation. Chloride anion attack carbocation, give you the final product. And here is the SN1 mechanism. Note that the protonation of hydroxide to form a better leaving group is very common in acidic condition. If the alcohol is primary or secondary, thionyl chloride or phosphotribromide are needed. The reaction undergoes SN2 mechanism. First, hydroxy, a poor leaving group, is converted to a better leaving group. So this is a good leaving group, and this is also a good leaving group. The second step, chloride or bromide attack on the back of the leaving group leave at the same time and give you the final alkyl chloride or bromide products. In summary, tertiary alcohols react with strong acid, hydrogen chloride or hydrogen bromide, to form alkyl halides. The reaction is SN1 reaction. Secondary or primary alcohol react with the thionyl chloride or phosphorus tribromide to form alkyl halides, and the reactions are SN2 reaction. The poor leaving group hydroxy in alcohols can also be converted to tosylate. As we know, tosylate is a great leaving group. So this makes the substitution reaction possible to form alkyl halides. The next reaction we are going to discuss involving alcohols is elimination or dehydration to form double bonds. The overall reaction of a dehydration reaction is a hydrogen atom and a hydroxy group combine to form a water molecule, and at the same time an alkene is produced. Similar to the preparation of alkyl halides, where a tertiary alcohol undergoes SN1 reaction with hydrogen chloride or hydrogen bromide to form alkyl halides. A tertiary alcohol in acidic condition undergoes E1 elimination, and the products follows Zephyr's rule, in which the more branched one is the major product. Here shows the three-step mechanism. The hydroxy group in acidic condition is first protonated. A better leaving group is formed. Next, the leaving group leave forms a carbocation. Water serves as a weak base. Water deprotonates a hydrogen atom adjacent to the carbocation. A double bond is formed. Primary alcohols undergo E2 elimination, but the E2 elimination requires a strong base. And in this case, we cannot change hydroxy into water as a beta leaving group, because to change into water, we need to add acid solution. An alternative is to convert hydroxy into tosylate as a good leaving group, followed by a strong sterically hindered base. A combination of phosphorus oxychloride with pyridine is a commonly used dehydration reagent. When an alcohol is treated with this combination, a hydroxy group and a hydrogen atom at the neighboring carbon is removed. A double bond is formed. Note that one of these hydrogen may also be removed. A double bond may form here, but this double bond is a more branched one, and so it's more stable. This reaction undergoes E2 elimination. First, the hydroxy oxygen attack phosphorus oxychloride to form a beta leaving group. Pyridine serves as a base which deprotonates a neighboring hydrogen, and leaving group leave simultaneously, give you the double bond. So pyridine is both a solvent and a base in this reaction. In summary, tertiary alcohol can undergo E1 elimination in acidic condition, and the product obeys Zephyr's rule, and that is the more branched alkene is the major product. In primary alcohol, the hydroxy group can be converted to tosylate, followed by E2 elimination. The combination of phosphorus oxychloride and pyridine is the common reagent for dehydration. A hydroxy and the neighboring hydrogen can be removed. A double bond can be formed. We have discussed the two types of reactions involving alcohols. One is a substitution reaction to form alkyl halides, and the other is dehydration or elimination to form double bond. Next, we are going to discuss the oxidation reactions to form carbonyl compounds. You already learned the two reducing reagents, and that is sodium boron hydride, lithium aluminum hydride. They all have many hydrogens in the formula. On the opposite side, oxidizing reagent contains lots of oxygen. And you saw this potassium permanganate before, and this has been used to oxidize alkyl benzene, for example CH2CH3, into benzoic acid. Okay, so potassium permanganate is a strong oxidizing reagent. Today we learn two more: chromium oxide, sodium chromate. All right, so by treating one of these oxidizing reagent, a primary alcohol first lose two hydrogen into aldehyde. Okay, and then this hydrogen can be replaced by a hydroxy group to form a carboxylic acid. So for primary alcohol, carboxylic acid is the final product. If it's a secondary alcohol, then losing two hydrogen give you ketone. Okay, and because ketone this carbon does not have hydrogen, it cannot be oxidized further. So that's the final product for secondary alcohol. Okay, ketone is the product for secondary alcohol. If it's a tertiary, then no reaction occurs. The carbon does not have hydrogen. So tertiary alcohol cannot be oxidized. Here shows an example of primary alcohol is converted to carboxylic acid using chromium oxide or sodium chromate. As we saw in the last slide, this reaction first forms an intermediate. So in this case, the intermediate is an aldehyde, and this aldehyde can be further oxidized to the carboxylic acid. So here is a question: can we have a method that can stop this reaction at this stage, only produce aldehyde without being further oxidized? Okay, and that can be achieved by a new oxidizing reagent called des-Martin Pyridine. And this is a mild oxidizing reagent. The structure has an iodine connect to benzoic acid with 3 acetate. Okay, by treating with this oxidizing reagent, a primary alcohol is converted to aldehyde without being oxidized to carboxylic acid. An alternative reagent is called PCC, pyridine chlorochromate. Okay, so by using either of these two, PCC or des-Martin Pyridine, a primary alcohol is converted to aldehyde, not carboxylic acid. Here briefly shows the mechanism of oxidation reaction. Alcohol first attack chromium oxide, all right, and followed by base deprotonate hydrogen. Aldehyde is formed, and this mechanism is E2 elimination. Aldehyde further be oxidized to carboxylic acid. Okay, for des-Martin Pyridine, alcohol again attack iodine, and rearrangement give you aldehyde, and reaction stop here. When a secondary alcohol is oxidized, the product is a ketone, and ketone cannot be further oxidized, and therefore whether you use a stronger oxidizing reagent such as sodium chromate or mild oxidizing reagent des-Martin Pyridine, it doesn't make a difference. They all becomes a ketone. In summary, we introduced several oxidizing reagents. When strong oxidizing reagents such as potassium permanganate, chromium oxide, sodium chromate are used, a primary alcohol becomes carboxylic acid. A secondary alcohol becomes a ketone. A tertiary alcohol does not react. When a mild oxidizing reagent such as des-Martin Pyridine, PCC, are used, primary alcohol give you a aldehyde. Secondary alcohol still give you a ketone. Tertiary does not react. Sometimes hydroxy groups may interfere with other functional groups to perform chemical reactions. In these cases, we need to protect the hydroxy group or alcohols. For example, this molecule is Alkyl bromide, which can be used to make a Grignard reagent. However, this molecule also contains a hydroxy group. The hydroxy group will react with a Grignard reagent. And in other words, the hydroxy will prevent the formation of Grignard reagent. So in this case, hydroxy needs to be protected before the reaction proceeds. Alcohols can be protected by forming trimethyl silyl ether, or OTMS. And this is achieved by treating an alcohol with chloro-trimethylsilane. Since OTMS is inert to many reactions, for example, it does not react with Grignard reagent, and therefore alcohol is protected. In the end, alcohol can be regenerated by simply treating the OTMS with acid solution. The reaction follows SN2 mechanism. Reaction requires a base, usually a tertiary amine. This amine deprotonates hydrogen from alcohol, and the oxygen attacks silicon. Chlorine serves as a leaving group leave, gives you OTMS. As we know, tertiary alkyl halide cannot undergo SN2 mechanism. However, silicon is much larger than carbon, and the large size of this silicon allow the attack from oxygen, and the SN2 is possible. Example, how to perform the following transformation. And note that the product is an alcohol with 5 carbon and the reactants 3. So in this chapter, we learned one way to make a longer chain alcohol is to add Grignard reagent to an aldehyde. And so this product may come from two parts. This comes from aldehyde, and this comes from a Grignard reagent. And so a aldehyde, okay, like this, and a Grignard reagent, so that this carbanion attack aldehyde, alkoxide protonation, and that give you this 5-carbon alcohol. Okay, so the question now is, how do you make this Grignard reagent? And we learned that Grignard reagent can be made by Alkyl bromide, that's the reactants, plus magnesium. Then we notice that there's a problem. There's a hydroxy in the molecule, and the hydroxy will interfere with the Grignard reagent that just made. Okay, therefore this alcohol has to be protected first. Here shows the synthetic procedures. First, the alcohol is protected by treating with chloro-trimethylsilyl with a tertiary amine, and the product is OTMS. This trimethylsilyl ether is inert to many reactions, including Grignard reagent. So the next step is to make a Grignard reagent by adding magnesium metal, and the Grignard reagent is synthesized. The Grignard reagent reacts with a aldehyde, in this case ethanol, followed by acid solution, give you the alcohol. So after this chapter, you should be familiar with this method to prepare alcohols. Okay, so last step, remove the protecting group by adding acid solution. The alcohol is regenerated. Phenols are similar to alcohols. The industrial process to synthesize phenol starts with cumene. Cumene is oxidized by oxygen to form a hydroperoxide, which treated with acid solution give you a phenol and an acetone. As we learned in chapter 16, the hydroxy group is a strongly activating, ortho and para directing, make phenols highly reactive substance for electrophilic halogenation, nitration, sulfonation, and Friedel-Crafts reactions. When a phenol is oxidized, the product has two carbonyl groups on the para position, and this is called a quinone. In carbon-13 NMR, for alcohols, the carbon bonded to oxygen has a chemical shift between 50 to 80, and the hydrogens connect to this carbon has a chemical shift between 3.5 to 4. In summary, alcohols can be converted to double bond by elimination. A tertiary alcohol can react with acid, undergo E1 elimination. We introduced a very important dehydration reagent, and that is phosphoroxychloride combined with pyridine. One way to convert the primary alcohol into double bond is convert to tosylate followed by E2 elimination. Alcohols can be protected to form trimethylsilyl ether. Alcohols can be converted to alkyl halide by substitution reaction. For tertiary alcohol, we use HCl, HBr. For primary secondary, we need thionyl chloride phosphorotribromide. The mechanism is SN2 reaction. Alcohols can be converted to ketones aldehyde carboxylic acid by oxidation reaction. Tertiary alcohol does not work. Secondary alcohol always form ketone. We can use potassium permanganate, chromium oxide, or sodium chromate. If it's a primary alcohol, we need to pay attention to the oxidizing reagent. For mild oxidizing reagent such as DMP or PCC, the product is aldehyde. The reaction stops here. If it's a strong oxidizing reagent, such as potassium permanganate, chromium oxide, sodium chromate, the product will be a carboxylic acid. Homework: please work on problems 17.12 to 17.16. Since there aren't many questions in this section, it would be helpful if you try to do more additional problems, particularly on synthesizing alcohols and the reactions of alcohols. Also, practice mechanisms.